Hello and welcome. This is the pre-lecture video to the second half of Chapter 11. We'll be talking a little bit more about intermolecular forces, phase changes, and phase diagrams today. So let's look at some different types of phase changes. Of course, we can imagine a solid melting to a liquid. We call it the melting fusion point. And so you have the melting process when you melt into the liquid, and then obviously the freezing or fusion process when you go back to the solid. We can vaporize the liquid into the gas form, and then obviously you can condense the vapors back into the liquid form. Likewise, some substances can undergo a direct sublimation from the solid phase directly to the gas phase, and then they can also have a deposition back to the gas phase, where the gas particles are deposited back into the solid phase. So we have to have energy absorbed by the solid to melt into the liquid, and likewise we also have to have the liquid absorb heat in order to vaporize into the gas. Likewise, the same if the solid's going to transition to the gas phase. Again, we have to have the absorption of energy by the system, by the molecules undergoing the phase change. And then likewise, if you have a gas phase substance vaporizing back to a liquid phase, energy is being given off during that process of condensation or deposition, or from freezing the liquid back into the solid. There's a relationship between the heat or enthalpy of fusion, the heat or enthalpy of vaporization, and the heat or enthalpy of sublimation. So the delta H of fusion is often called the heat of fusion, or like I said, the enthalpy of fusion. Delta H of vaporization versus the delta H of sublimation. So sublimation is, of course, solid to gas. Vaporization is, of course, liquid to gas. And fusion is the solid to liquid or liquid to solid phase change. So the delta H's are the same for each of these transitions, whether you're going liquid to gas or gas to liquid, for example. It's just a matter of whether or not your sign is positive or negative. So liquid to gas, energy has to be absorbed, so that's going to be delta H greater than 0. Solid to liquid, delta H will be greater than 0. Heat has to be absorbed for that transition to take place. Likewise, the same for sublimation, it has to be greater than 0. Now, if you're going gas back to solid, gas to liquid, liquid to solid, if you're flipping these reactions around, then obviously they become negative in terms of exothermic reactions. So gas to solid, gas to liquid, or liquid back to solid, these would all have negative delta H's. You'd all lose heat as those transitions are taking place. But now notice the relationship between fusion and vaporization. If you add these together, those equal your sublimation delta H. So you can see in the figure, 5 plus 24 is 29, 7 plus 29 is 36, 6 plus 41, etc. 29 plus 58 is 81. And so all that's going on here, if we use, let's use water as our example. So if we have water solid going to water liquid, that's the delta H of fusion. And then water liquid to gas. So the liquid's canceling out here. This is the delta H of vaporization. If we add these reactions up, H2O solid to H2O gas, that's our sublimation. So our delta H of sublimation, since we've added these two reactions up, will just be the delta H of fusion plus the delta H of vaporization. So it's just a Hess's law summation on why the two added together yield the enthalpy of sublimation. We can look at a heating curve. This heating curve is describing the temperature of a substance as it's being warmed, and so as the temperature is warming, heat has to be added to increase the temperature or to accomplish a phase change. And so ice below its melting point has to warm up to the melting point, and so there'd be heat associated with the warming of the liquid. This would be due to the specific heat of ice. Now, the specific heat of ice is actually different than that of liquid water. So liquid water going from 0 to 100 goes by the specific heat of liquid water, which has a different specific heat than ice. But we also have to get through the melting point. So we have to get through the actual delta H of fusion. So we have to have the substance actually melt. B to C involves heat being absorbed without causing a change in temperature, but the phase changing from the solid to the liquid phase. So delta H of fusion is showing that to go from 0 degrees with the substance being a solid, 0 degrees substance being a liquid, that depends on the magnitude of the delta H of fusion. Now, it usually doesn't take as much heat to melt a substance as it does to vaporize. And the explanation is quite simple. When you melt a substance, you're only breaking some of the intermolecular forces between the molecules, but you're still being left behind with a lot of the intermolecular forces intact. But when you vaporize a substance, you're breaking all of the intermolecular forces. So it takes a little bit more energy, or usually a lot more energy, to break all the intermolecular forces and vaporize the substance. So for most substances, you find the delta H of vaporization to be greater than the delta H of fusion. Just in general, because we're breaking all the intermolecular forces to vaporize, only some of them to melt. And so then once you go through the phase change process, following the water warming up from 0 to 100 by the specific heat, so you can kind of look and see that not much heat has to be added to get from 0 to 100. So you're not adding too much heat to warm up the liquid. Then it takes a lot of heat to get through the enthalpy of vaporization step. And then finally you would have the CS of steam being different again. The specific heat of a substance usually does depend on its physical state. And so the CS of ice is a little bit different than the CS of liquid water, which is a little bit different than the CS of steam. So you could imagine, it's kind of a boring problem, but you could imagine taking a certain quantity of ice and figuring out, okay, how much heat does it take to warm it to its melting point? How much heat does it take to get through the melting point? How much heat to go from 0 to 100? How much heat to get through the vaporization? How much heat then to warm up the vapor? So if you want to go from, say, minus 25 to plus 25 degrees C, ice, to vapors, you just have to consider 3 different temperature changes, 2 different phase changes, and add those quantities together. Supercritical fluids are how we describe gases when they sort of begin to liquefy as they are pressurized. And we get to a point where the gas really behaves kind of like a liquid-gas hybrid, so we call this a supercritical fluid. So the temperature beyond which a gas cannot be compressed is called the critical temperature, and then the pressure needed to compress this liquid to this temperature is called the critical pressure. The state beyond this temperature would be called the supercritical state. So you can actually keep pressurizing, if you will, the substance. It just no longer would be described as being a gas. So the supercritical fluid would take on properties similar to both the gas and the liquid. So this shows the supercritical, or the critical temperature and pressures for things like nitrogen, argon, O2, all the way up to some polar substances like H2S, ammonia, and water. So what you can see is that the critical temperature is related to the intermolecular forces. The stronger the intermolecular forces, the more of the gas, and the higher you can take the temperature and the pressure of the substance and still be in a gas phase regime. And so the critical temperature kind of goes the same with this similar trend as the boiling point, melting point trends. So it's proportional to the strengths of intermolecular forces. And so beyond these temperatures, so if you get to a temperature and pressure beyond both of these values here, then you would describe that state as being a supercritical fluid. Now there's some applications of supercritical fluids, not really many that they're all that useful for us to understand here, other than maybe the idea that they serve as a solvent. For example, supercritical carbon dioxide sometimes is used to remove things like caffeine from coffee, because it turns out to dissolve caffeine relatively effectively. So you take a sample of CO2, pressurize it with coffee, the caffeine, and probably some other flavoring, because I've never had good decaffeinated coffee, but you probably lose the caffeine and some of the flavorings of the coffee into your fluid, and then you can separate the rest of the coffee from the fluid and then depressurize the gas, and then you're left behind with the caffeine that you can maybe do other things with. So maybe you'll make some other products out of the caffeine, or maybe you'll just dispose of it or do whatever you want to do with the caffeine once you separate it from your coffee. So many liquids can be considered to have a vapor pressure. So at any temperature, some liquid molecules may have enough energy to escape the surface and become a gas. And depending on the liquid and the substance, this vapor pressure may be higher or lower. One of the things you can think of is a liquid that has some sort of an odor associated with it. It's probably the molecules escaping the surface, so it's probably the vapors of the liquid that you're actually smelling. You can imagine this with a liquid like ethanol, or maybe even a solid like naphthalene, one of the ingredients in like mothballs. The sort of scent that you might pick up maybe from vanilla is also the vanillin molecules and vanilla that are escaping the surface of the solid. So this works with solids and liquids where they can have a vapor of the molecule with the molecules escaping the surface of the substance. So as the temperature rises, the fraction of molecules that have enough energy to break these intermolecular forces increases. So you can think of the intermolecular force between, say, ethanol molecules is whatever it is. There's a certain attraction between adjacent molecules in ethanol. As you increase the temperature of an ethanol sample, more and more of the molecules begin to have an energy high enough to break the intermolecular attraction between the molecules. So those molecules can escape the surface and create the vapor pressure above the liquid. As more molecules escape the liquid, the pressure increases. So what this graph is trying to, or this picture is trying to demonstrate, is taking some ethanol, adding it to a container. And so initially when you add it to the container, you have an atmospheric pressure of whatever air was initially inside the container plus your ethanol. Then eventually the pressure increases inside the container as your ethanol molecule inside the container begins to, the liquid molecules begin to escape the surface. And so you could warm the substance up and see that the pressure inside the container goes up even more because you're giving more energy for the ethanol molecules to escape their surface. So liquid and vapor at some point, they'll reach a dynamic equilibrium. The idea of what a dynamic equilibrium is relatively important for Chem 1220, for some different type of problems that you'll study. What this means is you're going to always have a rate of molecules escaping into the gas phase, as you then have a rate of the molecules returning back to the liquid phase. And so you reach a point, though, where you're at a stasis, where the amount of molecules that are in the gas phase is relatively constant. So you'll have some molecules still escaping the surface and some molecules regaining into the surface, but those taking place at rates that are equal to each other. Before this dynamic equilibrium is established, like right when you first add your ethanol to the container, you're going to have a much faster rate of the molecules out of the liquid and a slower rate of the molecules into the liquid, just because you don't have as many molecules in the gas phase at this point. So you can imagine that this reaction rate will start to slow down, and then the returning rate will pick up until they're equal. When those rates are equal, when the rate of escape is equal to the rate of return, then the substance is at a dynamic equilibrium, and the rate or the pressure of the system would be constant. Now, it doesn't take long for this sort of dynamic equilibrium to establish. It's usually relatively fast. You can imagine adding ethanol to a container, shaking it up a little bit, and then venting it and kind of seeing, okay, you have relatively quickly an increase in pressure due to the vapor pressure of the ethanol. So boiling point is a consequence of vapor pressure. So a liquid boils at a temperature at which its vapor pressure equals atmospheric pressure. So for the case of water, we know that's 100 degrees C. So at 100 degrees C, without knowing anything, you know water's vapor pressure must be standard atmospheric pressure, 760 torr. So if you go below 100 degrees C, it ends up being an exponential relationship, but the vapor pressure lowers as we lower the temperature. So we get an increase in vapor pressure as we increase the temperature of water. Likewise, the same for ethanol, though ethanol has a lower boiling point than water. I don't know if you would have guessed that per se, but ethanol just has a slightly weaker hydrogen bond. Well, water forms two hydrogen bonds because it has two hydrogens attached to one O, and ethanol only has one H attached to one O. So ethanol just sort of doesn't have as strong of an intermolecular force because it lacks an H bond that water has by having two H's attached to an O. Now, ethylene glycol, one of the major ingredients in antifreeze, has two OH groups. So it's like ethanol, where you have a CH2, then OH, another CH2, but then instead of being CH3, CH2, OH, you have two OH groups on adjacent CH2 molecules on an ethane type unit. And so now this molecule gets two hydrogen bonds, but also some added dispersion forces due to having the two CH2 groups in the middle of the molecule. So this molecule has a boiling point of about, I believe it's about 200 degrees C, somewhere in that ballpark. And so as a result, it has a lower vapor pressure at relatively low temperatures. And so water has a higher vapor pressure due to having weaker intermolecular forces, whereas ethylene glycol has stronger intermolecular forces and hence a lower vapor pressure. So vapor pressure itself, if you think of strengths of intermolecular forces, as intermolecular forces go stronger, the vapor pressure of a substance becomes smaller. And so if we do the opposite, if we look at a substance that has weak intermolecular forces, diethyl ether is such a compound. So diethyl ether would be CH3, CH2O, CH2, CH3. This molecule here has relatively weak intermolecular forces, no hydrogen bonding in the molecule, It's big, but not big enough to counter the H bonding in molecules like ethanol, water, and ethylene glycol. So it has a lower normal boiling point. Its normal boiling point is about 35 degrees C. And then it has, therefore, a much greater vapor pressure at relatively low temperatures. So you could compare it like room temperature, the vapor pressure of water. We saw an example, it's about 25 torr. Ethanol looks to be maybe a little higher, maybe about 50 torr. Whereas diethyl ether looks like it's very near boiling at even room temperature. This might be in the next slide, but just in case it's not, one of the ways you can actually boil a substance at a lower temperature would be to reduce the surrounding pressure. So if you go to a lower pressure, like let's say you go to a pressure of 300 torr, you can then say, well, what would the boiling point of diethyl ether be? It would be well below room temperature for diethyl ether. It would be for ethanol, probably about between 55 and 60 degrees, somewhere in that range there. I didn't draw a very good line. So at 300 torr, for the case of water, we'd have a vapor pressure of about, or a boiling point of about 70 degrees for water at this reduced pressure. So if you want to decrease the boiling point of a substance, what you would want to do is decrease the surrounding pressure. So maybe put a vacuum pump some of the air molecules away from in the gas vapors as well as they're being produced by the vaporization, but reduce the surrounding pressure to lower the boiling point. Another thing you can do is actually increase the pressure to increase the boiling point. So you probably, well, maybe not, have seen a pressure cooker used in a kitchen. What that does is it increases the boiling point of water, your primary solvent for cooking. So it increases the boiling point of water beyond 100 degrees C so you can cook foods faster. So if it takes 2 hours to cook a roast at 100 degrees C, maybe it only takes an hour if you can increase the temperature of water to 120 degrees by increasing the surrounding pressure using something like a high pressure cooker. And so this figure here shows the relationship between vapor pressure and temperature. And so we saw earlier that on the previous slide that there's an exponential relationship. In mathematics, if you have an exponential relationship, then you might want to do something like take the natural log of the pressure versus 1 over the temperature, and then you should be able to get a straight line. And so what we could do with this approach here would be study the pressure, the vapor pressure of a liquid versus the temperature. So if you had some means of doing this, study the temperature at a few different temperatures, and then see how the vapor pressure increases accordingly, and then do a graph of the natural log of pressure versus 1 over T, then you should yield a line where the slope is equal to the negative delta H of vaporization divided by R. So we have a negative slope here for this line going downward, and then so our delta H of vaporization should still come out to be a positive quantity for this type of an approach. So we have a phase diagram shown here. So we have a solid, liquid, and a gas. So what we're trying to do with the phase diagram is understand at various pressures and temperatures, what phase can we describe a substance to be in? And so let's take a look here. So if we at relatively low temperatures, so this is like 0 Kelvin, low pressure, then what we have is a solid that can directly transition to the gas phase. Then substances usually have a triple point at some pressure beyond 0, so at some relatively high pressure greater than 0. If that's where the triple point is, then at pressures below that value here for your triple point, then you can sublime a solid directly to the gas phase and deposit a gas directly into the solid phase. But if you go to a pressure above this point, then you can have the normal melting into a liquid, and then the liquid vaporizing into the gas. The critical points mentioned here, so beyond this point here is our supercritical fluid state. So at this state here, what you have is essentially a liquid that's conforming to the shape of its container. So you get some interesting, perhaps, solvent trends. So the substance doesn't explode or doesn't do anything funny necessarily just because you pressurize it or pack a lot of gas into a container. It just turns into something that behaves kind of like a liquid and maybe is useful for replacing like an organic solvent with some type of greener application. So if you can find a way to use CO2, maybe you pull it out of the atmosphere and use that as a solvent for some types of chemical reactions that you're doing, you can remove CO2 from the atmosphere and then find something useful to do with it instead. Okay, so we can also think of pressurizing a substance. So if we take a gas, imagine take a gas at this sort of temperature and pressure here. It doesn't matter what the temperature and pressure is per se. Just imagine on our graph we're here, pressurize the sample goes up. So we pressurize the sample, it turns into a liquid, and then if we keep pressurizing, the liquid is compressed into a solid. And so most substances kind of behave this way, that if you take most gases, you can either directly compress them into the solid or compress them into the liquid and then into the solid state. Of course, if you're way over here, you compress this gas, pack more gas into the material, or push down on the piston, maybe the substance starts to behave more like a supercritical fluid. The phase diagram of water is interesting in a sense that if we pick a phase here and pressurize, we can go to the liquid state and then stay a liquid. Likewise, if we start over here, pressurize, and we pressurize to the solid phase, and we keep pressurizing, and oddly enough, it turns into a liquid. And water is very strange in that regard, in that not many substances behave this way, where the liquid is actually more dense, or in some parts of the curve, more dense than the solid. We know this to be true for water because ice floats in liquid water, so we know ice is less dense, but the hydrogen bonding nature of water makes it adopt a particular crystal structure that the water molecules are actually a little bit further away from each other in solid form than they are in the liquid form. So in the liquid form, water molecules manage to get closer together than they do in the solid phase, hence having a greater density. So this curve here is sometimes called a negative melting point curve. So a negative melting point curve just means that the solid is less dense than the liquid. Now, not many substances fall into this category. Water is kind of unique in this regard. And so water above its critical values exists as a supercritical fluid. Like substances behave, we can identify its triple point. Its triple point is well below atmospheric pressure. So at atmospheric pressure 1 atm, water can undergo the normal solid to liquid to gas. So when you're imagining a substance changing temperature, that's going left to right on our graph. So changing temperature, go left to right, pressurizing, go up and down. And so then you might, on a given chart, look for 1 atm because that'll let you know what phase changes are possible for the substance at ordinary standard pressure on Earth. Now let's look at CO2, because CO2 is kind of interesting. It's our classic case of a compound that sublimes, and it sublimes because its triple point has a triple point pressure well above standard atmospheric pressure. So at 5 atm, we'd have to pressurize CO2 to above 5 atmospheres in order for solid CO2, in order for dry ice to melt into a liquid phase, and then for that liquid to transition to a gas and undergo what we might ordinarily think of as our standard solid to liquid to gas conversion. But at 1 atmosphere, so at 1 atm, CO2 transitions directly from the solid to the gas phase. Okay, so that's pretty unique. For at atmospheric pressure, we can take a piece of dry ice. This critical point here, or this phase change, takes place at about minus 78 degrees C. So about minus 78 degrees below zero in Celsius, CO2 would transition from a solid to a gas, bypassing the liquid state just simply because 1 atmosphere is below that triple point pressure of CO2 of about 5 atmospheres. Okay, now I don't expect you to memorize any of the particular numbers on these graphs or whatever, but I expect that what we can do is find the critical point, find 1 atmosphere, identify the normal phase changes that would take place at 1 atm. So our normal boiling point, our normal melting point, our normal sublimation point, these are the points of which phase changes arise at 1 atmosphere of surrounding pressure. So we're just noting the temperature of which these transitions take place on the temperature scale from a graph of this sort. And so we get a sense of under what types of pressure and temperature conditions does a substance exist as a solid, liquid, gas, or as one of these supercritical fluids. Okay, that's all for our pre-lecture video for the second half of Chapter 11. We have just one more pre-lecture video to go, and if you're counting, depending on when you're watching this video, perhaps 2 more lectures to go in the class. So we're nearing the finish line, almost there. So thank you for the attention. Look forward to seeing you in class.